Okay, I'm gonna make it simple after 1 hour session on neutral correlated agreement. Actually, I will not focus so much on my concrete findings of my work. I will focus, let's say, one of the aspects that led my quite technical work on proof acceptance of protocol secure. So I call it just here nodal correlated agreement because left and right. So okay, sorry. Okay, just recap. What's correlated agreement? What's a correlated agreement theorem? A cat.
So you don't even have a picture of a cat.
It's a correlated agreement. Okay, so given two words, F is finite field, so finite field values work over domain D. If with notable probability, the random linear combination C is the scalar I choose. So the probability is to the scalar I choose it from. For few of these C's, these random linear combinations close to the code, then also, and I just encode and cipher correlated agreement as the vector-wise, the interleaved code, interleaved word correlates with a pair of polynomials. That's what correlated says. So you go just vector-wise equality. Okay, so that's correlated agreement. And the thing is, if you just go all the theorems, starting from the very first up to the proximity gaps paper, the way it's stated is, I see it, yeah, I did the wrong compilation here, so I cannot click through. So it's always the full slide, sorry. So as it's stated, it seems like that the agreement sets between the random linear combination and its close polynomial or closest polynomial, to make it simple. That this agreement set, and the agreement set where we have correlated agreement, the left-hand side in your Egon slides, that there is no relation between them. That's why you also see in Egon slides the first picture, right? You know, on the right-hand side we have the green area here, and then we have the green area of correlated agreement in a different place. But the thing is, that's only seemingly the case. That's only seemingly the case. It's just the way how it's stated. If you go behind the curtain, if you look into the proofs, there's one, let me just go back. There's one central technique, or let's say one central property that is obtained before doing the final step that did uses correlated agreement, and that's correlated agreement, what I call collinearity of proximants in short. And what it says is the following. Again, we start with the two words U0 or U1 over the domain with notable probability. Small probability, the random linear combination is close to some polynomial that does nothing new yet. Then a fraction of these polynomials, of these proximants, lies on the line. So it gives you already also the pictures of how like proximity gaps is often explained when not using the notion of correlated agreement. So they lie on the line. And the funny thing is, sorry for this at once, I can recompile it. This is just one. No, sorry. Let's keep with it. So before I mess it up. Yeah. So okay. So the main thing is this is really the property from which you derive eventually correlated agreements, a stronger property, and the way how you do it. I would like to go through that proofs. It's really super simple elementary proof. And so collinear, so actually the way how correlated agreement is stated loses a lot of information. And the funny thing is, this elementary proof standard argument I will demonstrate. This works also under other in other environments. It's so correlated agreement under constraints. For example, when I proved base fault secure in LDR, I needed something I called the subcode correlated agreement theorem, let's make it short, a correlated agreement theorem for constrained read-Solomon codes. Something like, if the random linear combination is close to a polynomial satisfying certain linear constraints, then the components of the linear combination have correlated agreement with P1, P2, which also are not just polynomials, but satisfy its same linear constraint. So that was really helpful to do the analysis of base fault, or Frobenius, and lately also Were. So also weighted cut, the weighted correlated agreement theorem is used by all these Frey-like protocols which have a correlated type of testing, like one sample where you check along use this one sample to check all these consistency relations between the foldings, not just of one round but of many rounds. So that is also considered like a correlated agreement theorem under constraints. And more lately, when I was writing the Stu-White paper, multi-domain Frey is a bit a pain in the neck when you consider it also in LDR, when we want to prove it sufficiently secure, or let's say meaningful secure, so that it meets your expectation in practice in terms of security parameters. There was even another correlated agreement theory on the constraints, which I call a set-specific cut was necessary. So, in short, this collinearity property, a fraction of the proximates are collinear. This will turn out to be, well, once I show you now this very elementary argument, turns out to be a local version of the picture we have when we have this from Elon's slide. It's a local version in some sense of mutual correlated agreement. And in fact, it turns out to be a component in all the proofs I know about mutual correlated agreement. These are the ones of Hadas, the Chinese team, or now most recently the Johnson bound for read-Solomon codes.
What does local mean here?
It's like, I will come back to that later in more detail, but it's just like that you only focus on a fraction of the approximates. So you focus on one line. The way how you prove mutual correlated agreement is in some sense you keep track of all the possible lines where your approximate might be situated on. So, and it's just on one instead. It's a kind of, you can say mutual correlated agreement theory, in other words, would be list correlated agreement theory.
Sorry, can you say that again?
List correlated agreement theory would be just a different name for it. Okay. Sorry for this blah thing. So just look at the top, yeah. So I will now give you somehow an intuition about the standard argument. So what is the presumptions? So this here is my collection of my fraction of proximates, which I found already. Oh, okay, super cool. The lie on the line, and the line is written as one polynomial plus c times the other polynomial, right? That's like yeah, the line. And then just consider the agreement set here. The correlated agreement set between my two words I start from and the two polynomials that span the line. And my claim is, if this fraction of approximate is large enough, that's the size of S, the index set for my, the size of S is larger than the domain size, N is the size of D, then we already know, and that's exactly the picture of Elon's slides, we already know that this correlated agreement set is equal, identical to one of the agreement sets in my collection of approximates. And it's really a three-liner. I mean, you can present it as a three-liner, yet it's always something I love to revisit. because there are refinements of this of all flavors, useful refinements. I just present here the simplest way to argue, and it is so assume it's not the case. What does it mean? So assume that all the agreement sets from my proximates that are on the line are not equal to A, to the correlated agreement set. It means there must be always a point outside A, right? And it means if you look at the correlated disagreement set, just the complement of A, it means AC, each AC has a point in there, right? Now fix a point in the disagreement. Let's forget for a second what I said before. So just look at the disagreement point, fix a point here, and ask yourself for how many challenges Z I can cancel out disagreement. Which means, you know, if you just take U0 in indeterminate Z, we don't know yet what it's going to be, and plus U1, the random linear combination symbolically, also the same for the two polynomials, because we said here at this point Z, they're unequal, these are different linear polynomials, therefore they can have only one root in common. Or in other words, that root, oh, let's say one root in common, that was a bit precise, so you can have only one value Z, where left and right is right hand side, right? Where they coincide. So in other words, there's at most one Z where this inequality gets equality. Or where we had correlated disagreement and end up with agreement of the random linear combination. So this is a separate observation. For any correlated disagreement, for any point of correlated disagreement, there's only one C that cancels out that error, that disagreement. Sorry. Yeah, and now let's go back. What is the assumption? Let's assume that it's not the case that A equals sum of the agreement sets of my proximates. So that means all agreement sets must be different to A. All agreement sets therefore must have a point in that set. Since these are agreement sets, but it's an agreement set. Means it must correspond to a Z that cancels out already something. Since this cancel out Z is unique, it means that for each different AZ, they must occupy different regions of my disagreement set. And consequently, there cannot be too many of these Z's. Actually, it's bounded by the size of the disagreement set. We don't know how large it is actually, so it's at least bounded by the size of the domain. And that's how you argue. So that means if, let's rewind here, so if all of my agreement sets would be different to A, then the set of, then the number of proximates I'm talking about cannot be large. And that's the argument. So if it's already that larger, then we must have equality of one of those sets, which is exactly the mutual correlated agreement setting in a local fraction, because if you look more carefully at the definition of mutual correlated agreement, it's like not thinking just about one line here, or a fraction of proximate that lies on one line. It's more like thinking about all the possible lines that might host different fractions.
Ulrich, if you work in a world where you do like Q0 plus Z, Q1 plus Z squared, like you have sort of a large number of things you're combining, you're going to have to add some factors here, right? Like you get like an...
Yeah, if you use not just random linear combination, linear but with powers of Z, it's the degree of the polynomial that runs into. Is that what?
Yeah. I'm just wondering, like, is that going to mean there's going to be a factor difference between the multi and the standard correlated agreement in sort of a more general case?
I'm not getting. Can you repeat?
Is that factoring really to a difference between the, like, because isn't this argument trying to go from correlated agreement to mutual correlated agreement?
No, this is just a general thing. Actually, when I conclude from, I have a fraction of approximates that lie on the line, but this is like the ancestor notion,
Oh, I see.
which shortly gives me, just in a few lines, correlated agreement.
I see.
And looking, just to give an idea, this is really implicit in almost all of the correlated agreement theorems. It starts from the Ligero publication, which only goes up to UDR over 3, so 2/3 of the mid distance, or the double Johnson cut, which was, I think, in the Fry paper, no, Fry improved paper. This improved worst case to average something, and then a 1.5 Johnson cut, which was in the deep Fry paper. It's all there. It's also for the Ritz-Solomon codes up to Johnson, and all the others that were subsequent. The only proof I saw where it's not needed is actually the UDR, the barely complex decoder analysis of the proximity gaps paper, because there you get it directly by algebraic divisibility. But this is just to name these words for those who went over it. Yeah. So you can say, for me personally, collinearity of fraction approximates, that's for me the ancestor notion, the core notion behind correlated agreement. And for that reason, I was also able to prove certain protocols. Of course, I agree with Giacomo and Elon. Mutual correlated agreement helps a lot in arguing in high-level protocol security. These protocols are complex, so we're happy to have something more easier. But strictly speaking, it's not needed for some of the protocols, at least the ones I was looking. The Fry-like protocol, Fry doesn't need mutual correlated agreement to be proven secure in LDR, and for the same reason, base fault and variance like work. So this is just in a short overview here. Yes, sorry again for the not properly rendered stepwise slides, but that's roughly what I wanted to say.
I have one question. Seems to me that maybe when we think of this correlated agreement problems, we tend to focus too much on the places in which the words coincide with code words, whereas the role of the number of alphas that satisfy the condition is neglected. Maybe in your slides, you were able to deduce that inequality of cardinalities because you were able to find a map from the complement of the agreement set with S. You had this bound in which the size of S was less than the size of the complement of the agreement set. What I'm trying to say now is, how do we control that in case we have more sets?
It's a bit more difficult, of course. And actually, like, I needed to learn that global view. This is the question, like, where you could think of several lines where different fraction of approximates lie on and how to incorporate that. It's not trivial, it's not obvious.
No, it's not obvious.
So, in my recent proof for up to Johnson for Ritz-Solomon codes, it's a little bit more obvious because these lines you could have are predetermined somehow algebraically by the factors of the Google-Swami-Sutterlich polynomial. So you see them per se, but it took me a while. I got from Hadas like a preprint of her work, pre-Katam or so, and I was banging my head on the table for like a day or two to understand this global approach even like that you have in a notion of mutual correlated agreement, like that could be everywhere. That was for me going through the old school, a more modern, a new way of thinking about it, which was really hard to switch for me.
I have one more question. What was it? Just, it's okay. I'm good. Anyone else?
What can we do about Johnson? Give us your.
I'm the wrong guy to ask here, so you need to really ask people like Swastik and.
No, I'm joking with that.
So I really don't have any intuition, and I personally, the first thing I would do, just to say something, is look at the publication that does list decodability for random codes up to capacity, because for me, even this, I don't know why it's not possible, you know. So,
I remember. What was the role of the bound in these slides?
which part?
The ones that you just presented, like where the delta appears.
I'm not sure if I understood the question. So which bound?
From your proof,
I'm trying to.
where's the regime?
The thing is to obtain, to find a line where a notable fractional property approximates line alignment. That's already actually, if you have this, you've finished essentially. So the difficulty is really that there is that a fractional approximate, to prove that there's a fractional approximate which is collinear. That's the difficulty, and that's where the regime enters.
Okay.
So
I get that.
that's really.
I get it.
So all I wanted to say here, most of the proofs really prove just the line, the existence of a line which hosts a sufficiently large fractional approximate. And then do always, that's why I call it standard argument, it's not my argument. You see it in all these proofs, maybe in different words, slight variations, but it is actually this.
I wanted to reiterate something that we mentioned before. So for the unique decoding, we have a very small error. It's kind of n over f, and that is very useful in some cases. It would be nice to have something that we can prove, let's say up to Johnson bound, that maybe does not preserve the exact distance. So you start with delta, you end up with delta plus some distance, okay? So you lose a bit in distance, but the error goes down, and then we can work over smaller fields. So even this relaxed version of correlated agreement or mutual, it doesn't actually matter. Even both of them would be actually very nice to prove it.